Hello everyone, this is Safo and welcome back. In this video we are going to learn how to analyze the stability of a control system using the Routh-Hurwitz Stability Criterion in MATLAB. This Routh-Hurwitz method allows us to determine whether a system is stable without explicitly calculating its pose. Okay, let's begin by writing the MATLAB code. First, we clear the MATLAB environment. These commands clear the command window, remove all variables from memory, and close any open windows. And next, we define the transfer function of the system. The numerator is 100. The denominator is s squared plus 10s plus 100. Using TF function, MATLAB creates the transfer function model. And here we display the transfer function. This prints the transfer function in the command window. Okay, let's plot the step response. Here, this allows us to observe how the system responds to a unit step input. Okay, and here we begin constructing the Routh-Hurwitz table. First, we print a title in the command window. And next, we store the denominator coefficient. These coefficients represent the characteristic equation of the system. Okay, now here we determine the size of Routh table. Here n is the number of coefficients. M is the number of columns required for the Routh table, and here we initialize the table with zeros. Okay, here we fill the first row. The first row contains the coefficient of the even power of s, and the second row contains the coefficients of the odd powers. Okay. Now MATLAB computes the remaining rows automatically. This loop, for to end, applies the Routh-Hurwitz formula to calculate every remaining element of the table. And here we display the complete Routh table. The entire table is printed in the command window. Okay. Next, we extract the first column. The first column is the K part of the Routh-Hurwitz criterion. Okay. Here we display it. MATLAB prints the first column separately for easier inspection. And then we check the stability. Here. If every element in the first column is positive, the system is stable. Otherwise, the system is stable and here unstable. Okay, and finally here visualize the pole location. Okay, this figure shows the locations of the system poles on the complex plan. Okay, let's run the program. Okay, in the command window, MATLAB first display the transfer function. You can see here. Then it prints the complete Routh-Hurwitz table. You can see here. After that, it's displayed the first column of the table. Here, first column of Routh table. Since every element in the first column is positive, MATLAB concludes that the system is stable and prints here system is stable. Okay, figure. Here, the first figure shows the step response. The response has a small overshoot before setting to its steady state value, indicating a stable unreamped system. The second figure shows the pole locations. Both poles are located in the left half of the complex plan, which confirms the stability predicted by the Routh-Hurwitz criterion. The Routh-Hurwitz criterion is one of the most important analytical tools in control engineering because it determines system stability directly from the characteristic equation without explicitly calculating the poles. Okay, thank you for watching, and I'll see you in the next video.